Yeah, so I am working on various aspects of dependent types of Haskell, and so this is a chance for me to tell you a little bit about what's going on with that, and tell you how much has happened, how much has not happened, and sort of what's going on. But first, let's start with the demo. And I apologize, the resolution on this is very different than what I was expecting. So, this looks good, but I need more than just this.
Max less?
Is this big enough for everyone?
Yeah.
Good. Okay. That's not what I wanted. Getting there. Okay. That's pleasant. So this is how dependent type Haskell was written yesterday. So here, I'm not going to get into all the detail of the code. We'll just sort of see the general shape of it. So here I have a natural number which is going to promote to the type level, vector over these natural numbers. And my goal here, by the way, is to write a standard dependent replicate function that gives me a length index vector of a certain known size filled with stuff. So I have this, okay, that's great. And then we need a whole bunch of singles and stuff. And then we got replicate, which actually isn't really so bad. And we take it in, and the interesting thing to note here is that the actual singleton I'm passing in is implicit, or as I'm going to call it, invisible. I think the word implicit has different meanings to different people, so I'm going to use invisible to talk about things that don't actually appear when you call a function. And so it passes this singleton invisibly. Of course, in replicate, you then have to make it visible again so we can pattern match on it. And sure enough, this works. There we have it. It actually makes that vector, if we can see it. But so that's how we did things yesterday. Let's see how we do things today. First off, notice the language extension. So we have the same vector, except here I haven't bothered with this nat type because let's just use integers. Why not? We have nil, we have cons. Replicate, we don't have any of that singleton stuff. That's great. Replicate here is actually pi quantified over n, which means it's available at both the type and term level. So it's available at both compile time and runtime. And over here, so it can be used at compile time because I mention it in vec an, and yet here I can actually pattern match on it. Even though it's invisible, I have this @ sign, which is an invisible override, so it allows me to use something visibly where the type expects it invisibly. So I can pattern match on it and return nil or otherwise recur. So that's great. And something went wrong here. Oh no. Unsupported. Okay, so this isn't actually implemented yet. At some point. This is when max and max don't necessarily play well together. So let me show you one more quick example of all of this. Okay. So now this is going back to this. This actually works today. What we see. I'm not kidding. It'll actually load. Oh, there it goes. And so here, using the singleton stuff that Jan talked about yesterday, I can actually promote fold R to the type level. And the goal here is to take a list of these vectors, and maybe each vector is of different length, and I want to concatenate the list into one big vector. So of course, my function, again, I don't want to go through all of these details, but it's going to actually have to fold plus over all of those things. And this works. So this is showing that what Haskell can do today is really quite strong. We can take this list, we can fold plus at the type level. But it's still better tomorrow, in that here, instead of bothering with this plus function that I have to promote, I just use plus. So we see in the type of v append here that I just take our normal plus operator and put a tick in front of it, and now I can use it in the type. Down here, of course, I could just use sum. That's more fun to promote full. I can do the same thing here. So using tick marks, just like we have with promoted data constructors, we can move these things up to the type level. And this may seem sort of like magic. The reason that I think that this is even possible is because we can do it with template Haskell today. So if we can do it in template Haskell today, we can do it in GHC tomorrow. And so that's why this, to me, doesn't feel like a pie in the sky game. So that's what this hopefully will look like. And now let's go back to the slides. I don't have to fight the resolution anymore. Okay. So let me just say, so you saw a bunch of Haskell code, and maybe there's a few of you out there saying, "This is not my Haskell. Stop doing this to my Haskell." Or Simon is saying, "Stop doing this to my GHC." But this is preliminary. So I've done some work, as we'll see, but I'm doing this to get input and to get feedback. So one thing that people often get worried about is all Haskell programs will still work. While talk a little bit about the possibility of combination checking, that's always going to be an optional feature. Another concern I've gotten is, will this kill all of our error messages? No, there's no reason to think that the error messages for non-dependently typed programs will change. So we want to really keep things the way they are. Those of you who can't see the thing on the bottom there, sorry about that. So that just says that let should not be generalized. Right now let isn't generalized over types most of the time, but still can be over kinds, and it really shouldn't. But no one does that. So we're going to talk a little bit about the surface design, and then I'll tell you exactly where we are. So first, sort of pie in the sky, exactly what I'm aiming for here. So here is the state of quantifiers, because I think to understand dependent types, we really need to understand how quantifiers work. So a quantifier, that's what introduces an argument to a function. These are the ways of making functions. Let me go through these different columns and explain what they're about. So dep is short for dependent. So that's can this thing that's being quantified over, the quantifyee, can that appear later in the type? So of course for all the answer is yes, it can. We're binding a new type variable. But for arrows, whether they're single or double, you can't. You can't mention those later on in the type. Is the quantifyee visible? Must we supply it when we're calling the function? So for all, the answer is no. Those are always inferred by unification. But for arrow, we do have to supply it. For double arrow, we don't. It's inferred by instance solving. When we write a type, must the quantifier appear in the type signature? So for all, the answer is no. Right? If we write a type that's just a arrow a, that's fine, and we'll infer the for all dot. And for arrow and double arrow, the answer is yes. We do need to actually write that in our types. And lastly, I think this might be the hardest one to understand. Is the quantifyee relevant? And to a first pass, you could think of this as not erased, but it's a little bit more complex than that. So for all, the quantifyee is not relevant because we can't then use a for all quantified type in a term. For arrow and double arrow, we can. So again, for double arrow, this is a little funny because we don't syntactically write it there, but it is around at runtime. The reason that relevance is not exactly the opposite of erasure is that we might want to specify this property one level up. So maybe we want to have a type family that we want to be sure is parametric in its kinds. And so we would want to say that the kind is irrelevant in the type. And so that's why this is not exactly erasure. But if you want to think of it as erasure, that's okay. Close enough. So that's what we have today. Tomorrow, we have this. And so the big thing this adds is pi. And so we have pi dot, which is the exact same syntax that we have today for all, and then some quantifiers and then dot. But it uses the word pi, like we saw in the demo. And this is dependent and relevant. So it's a thing that can be used both in a type and in a term. So that's the new amazing thing about dependent types. So here, that will still be solved by unification. I didn't really point it out very closely, but in that demo, the recursive call to replicate it didn't have to pass in anything because you could just figure out what the term or what the length should be by unification. Here, this also introduces pi arrow and for all arrow, and a full example of that's on the next slide. And that makes it visible because sometimes we actually want to force callers to pass things in. Sometimes it's easier to work with that way. And so this then sort of makes the zoo of quantifiers there. Okay, so let's talk a little bit more about pi. So here's another example. This is a slightly reformulated version of replicate that shows off slightly different features than the last version. So here I'm using an invisible quantification with pi, so I have pi arrow. Also like to point out, so it's not a mistake that that arrow is white and that one's green. This is the type constructor arrow, whereas that's just part of the pi syntax. Right? It's sort of not really the type constructor arrow on the left there. But I think it's convenient because we sort of see this flowing left to right, and we can see all the arguments. And so here, we can pattern match directly on this nat in the definitions for replicate. And here we can recur, and we get indifferent, we get suck and prime, and we can recur with n prime, and that will all just work. Okay, so that's dependent types, and then the rest is sort of talking about the other parts of Haskell that need to evolve to support all of these dependent types. So the first is that we're going to merge the type and kind levels. So I've talked about kinds of it, and that's when I say kind, I really want to. That's the thing that classifies types. But actually, a type can just classify a type. It's still sometimes convenient to use two different words. So in this world, type equals kinds. And that means that, say, type synonyms are now kind synonyms because they're the same thing. So this feature that sort of I have felt has been missing for a little while will come back. Not come back, will come in. Type families can be used as kind families. Gadgets can be promoted. So all of these restrictions right now around promotion are gone because there is no difference between type and kind, so everything gets promoted. By the way, this bit already is implemented and it works. So we have this now. Well, I do on my own stuff. So another thing that happens when types and kinds are the same is that kind variables and type variables therefore are the same. And so maybe in a poly-kinded type definition, I want to have an explicit kind variable k over here. And I can now put that in my definition. And so maybe for certain types this is more usable, maybe sometimes it's less usable. The implicit behavior still works. But now we can actually make it visible if we want to. So some of you might notice that the kind that I've assigned to t involves a pi over there. There are some good reasons for that, and you can ask me about it later. So the core language is the core language as proposed in last year's ICFP paper. There's quite a lot of detail there. I'm not going to get into that now. But actually what's in the paper is what I've implemented, and it works. And when I say works, I mean it compiles stage 2 of GHC. So it doesn't work just over trivial examples. Like GHC can compile with all of these things built in. Okay, a big question, something I'm still struggling with, is how on earth to parse this new language. It's not at all clear, right? Because if types can appear in terms, then we don't know when to sort of switch to the type parser as we're parsing arguments. So my best guess as to how to proceed is to combine the type, kind, and term parsers. Right now there are 3 separate parsers, and I want to make one parser to rule them all. Then the next question is how do I resolve names? And so we already have the idea that a tick mark can inject a term into a type, right? Because we can promote data constructors that way. I also want to propose caret for going the other way around. And then just like we have today, if a name is missing in the namespace that we first look in, we're going to look in the other namespace. So sort of ideally we'd have maybe one namespace like other dependently typed languages, but this is where we are. We have to work with what's there. A particular challenge comes around dealing with star. So if I say foo star int, what on earth do I mean? It's perfectly ambiguous. And so there seems to be no real way of fixing this problem other than just to get rid of star. Again, other suggestions are welcome. So I don't know if anyone noticed in those demo slides, maybe a couple of other places, I've had this funny U appearing. This is why. We can't really have star if we're going to combine the parsers. Or even just types and kinds, we can't have star. And in fact, this is why you can't promote type operators today. If you define a type that's written symbolically, you just can't promote that to be a kind, because the kind parser can't deal with it because of this. And so yes, the proposal is get rid of star and introduce U, short for universe, instead. Seemed better than other options like type in all capital letters, which is awfully angry looking, or type not in all capital letters, which will conflict with everyone who's written a compiler in Haskell, or just T, which conflicts with every example we ever write. So U seems to be the best idea. And we might want to even start this transition early. So a bunch of questions that I still have about this. Is this at all feasible? I have not stared hard at the parsers to figure out if this is possible. And parser engineering is not my strong point. So can we even do it? We saw an example earlier about how to override an expected invisible argument using an @ sign. Is that a good idea? Does that conflict with, say, as patterns too much? I don't know. If something is asking for a visible parameter, but we don't want to supply it because it can be inferred, should we just use underscore like every other language, or does that now conflict with poles? I don't know. Should we have the possibility of having a visible type parameter that's irrelevant? Maybe that's silly, I don't know. And what on earth would that do? And then there's a bunch of other things that I've barely begun to think about. So what do we do with dictionaries? Do they get promoted? I suppose we could. Unsaturated type families, there's some ideas that are in that were in the talk yesterday in my Haskell Symposium paper. What do we want to do about totality checking? Is this a good thing? Is this going to be too much trouble for people? What do we do about infinite terms? Do they become infinite types? The good news about all of these questions is we can just duck on all of them for now, right? If none of these features happen, dependent types will still be usable, at least at first. So and then as people start to use them more and more, they'll realize that these are real limitations, and we can try to solve them one by one. But we don't have to answer these today. Okay, so let me tell you what has happened. So as I've talked about, the type and kind language merge has done. Part of that was actually eliminating subkinding, which was a sort of a feature that not many people know about in GHC, about open kind, but I was able to get rid of it using an idea that mostly Simon developed really. Pi types, this is sort of my proposed way of doing pi types in GHC. So the idea being that we have our central type of types in GHC, and one of the constructors will now be pi tie. And this replaces the current for all tie and fun tie. Those of you who have played around with GHC API stuff. And of course, there's all different kinds of pi types. So we need to keep track of all of them. So there's the payload, which can either be named or anonymous. Apologies if so go down. And it can either be dependent or not, invisible or not, and irrelevant or not. And so all of these can be kept track of. So type inference. Type inference for existing code that currently compiles today. Type inference works for the new core language. That works now. And it works in some cases for code that cannot yet be done by GHC 7.8. When I start doing crazy things like promoting gaddis, the type inference falls over horribly. I'm still working on that. But I do have a type inference algorithm very closely based on Adam Gundry's work in his dissertation. And I'm working on sort of proof of correctness of that algorithm. A big difference from Adam's work is that I'm targeting outside in. And so I want to create constraints that look just like the outside in constraints, or almost just like the outside in constraints, so that we can use the existing constraint solver with few changes. And just like we saw in outside in, the outside in behavior, the goal is that it's a sound type inference algorithm and guess-free complete. And so again, the goal here, this ties back to what I was saying at the beginning, all current programs will still work. Type inference needs to remain as strong and as reliable as it is today. And so I've done quite a bit of work on this. It's not yet done, but I'm not stuck. It's just not done yet because time is finite. One big caveat here is that I don't have any plans right now of implementing higher order unification. I believe that dependent types are at least somewhat usable without this, and we'll see how bad that missing feature is when this is actually released. But that's something, again, that we can add later conservatively. So next steps. So I want to take what I have now. I've started to do the pi stuff. I think that was a misstep. I actually want to put that aside and instead go straight from merging what I have now back into master, if only to prevent the horrible merge times that I have right now. Then go back and finish pi to figure something out about the parsing all of this, and then I think we'll be ready to release. And somewhere in all of this, hopefully, maybe dependent on all of the other stuff, I can graduate. It may be related. And that's all I've got. So thanks.
You said the type inference algorithm is sound and guess-free complete? I
Yes.
don't know what guess-free complete means. Can you please explain?
Sure. So the idea is that it will find all types that you don't have to guess to find. And when I say guess, sometimes there might be a point. So for example, right now, if you have a function of type, say, FA arrow FA, where F is a type function, and we say we have some equations for it, we're not going to be able to figure out what A is because F is not injected. But actually, we could guess what A was. Maybe for in a particular use, if we said A equals int, it would work. But that takes a guess. And so so currently, GC avoids making any guesses of that sort. Another way to say it is it'll be backtrack free. Sort of the same idea.
Yeah, so I'm interested on what is there any problem with these other features that Haskell has that are not independent language, like open type families or constraint kind? These seem to be things that are not in Agdan or in Idris, and also not usually explained in outside in related literature. So I'm wondering whether you found any caveats.
Not yet. The reason I'm not as concerned about the type safety of all of this depends on the FC, on core. That's small enough that we can still prove it's sound. All of these other features end up getting to be sugared down into core. So then the other issue might be something like totality. But I'm not worried about totality because I'm not intending for Haskell to be a proof assistant or to be sound as a logic. I want to make sure ints never equal bools, but that's sort of the limit of that. And so if you write a program that causes GHC to loop, yeah, that was your fault. I'm not worried about that. And so it makes me a lot less worried about the interactions with other features than I might be if I really wanted totality.
I mean also like in the surface language, so you may find that this thing doesn't really work together, introducing one of these pi types, and then you have like an open type family, and then what you have is just unexpected.
I don't see. I mean, if you have a specific, we can talk about it later. But even with open type families, I've thought about that. I don't think that would cause a problem.
So it's clear you've got a lot of very hard problems here, but it's obvious the hardest one that you've shown us is what to call star. I want to suggest Unicode star.
Okay, one final question.
Thank you.
Okay, let's thank the speaker.